and welcome to this lecture. Today's lecture is basically the continuation of the last lecture. We are discussing in this lecture about regression analysis and correlation. We have seen in the last class there are some of these basic correlation, basic regression analysis we have seen, mainly that linear regression and those things. After that, we are in today's class we are going to cover that remaining part of this correlation analysis. First thing that we will go is the multivariate regression. In the last class we have seen that in the simple linear regression, what we have seen, there are one input variable and other one is that independent variable, that is y versus x. So, that if the x is your input variable and y is your target variable or your independent variable, then we have seen that how we can estimate the parameters for this regression, that regression model, and we have done how what are the original variance for the y, and then after the regression what is the conditional variance and all. Basically, we have also seen that through this regression what we are trying to do, how much, what is the extent of the variance of that target variable, that is y, is being reduced. So, here in this multiple regression what we do is that now this input variables are not 1, is more than 1. So, in that way, so we have to use the information of all those input variables and we have to develop a regression model for the target variable y. So, here the inputs are say x 1, x 2, x 3 and like that up to obviously x m. So, there are there could be some m variables what could be the input. Now, if we just try to extend that analogy of this simple linear regression to this multiple linear regression, first we will take that then from this one dimensional to the two dimensional, as we are discussing in this last class, that it is basically we are trying to take a straight line when it was a simple linear regression. But in case now if I just extend it, instead of one input, if it is two inputs, then basically it is a three dimensional space that you can imagine, and through that three dimensional scatter plots of those points, because one point now will correspond to the three entries, one is that from x 1, other one is x 2 and the target is y. So, basically one point is consist of this three pair. So, that is the three entry, the three data point x 1, x 2 and y. So, in this three dimensional scatter plot, basically we are trying to fit a surface. Now, depending on if it is a linear regression, then that surface will be a plane surface, and that's now that surface should be the best fit to that through those points. So, and through for that one, following the same principle of this simple linear regression, we have to find out that it should be fitted in such a way that the sum of square errors should be the minimum. So, this is basic transition from the simple linear regression to the multiple linear regression, and based on this we will see what are the theories involved in this. So, our we are continuing with that regression analysis and correlation, and as you have seen in this last class, that in this different types of regression that we have discussed, and there in the last lecture we have covered the linear regression, and here we will see where here today's class we will start with this multiple linear regression. So, and after we complete this one, we will see that what is the nonlinear regression, and this nonlinear regression can also be for the both the cases, maybe for the simple linear regression and also for the multiple linear regression. And then we will go through this correlation, and you know that this correlation we have discussed earlier also, but here in the context of this regression analysis we will once again see this aspect of this correlation. Basically, through this measure we are trying to identify what is the how perfect the model that we have selected. So, that we will discuss under this correlation. Well, to start with now, the for this multiple linear regression, as I was just telling that there will be one target variable, we generally call it as independent variable, sorry, that dependent variable, this is our target variable y, and there are more than one independent variable which are x1, x2, xm. So, let y be the function of m variables x1, x2 up to xm. Then the assumptions underlying the multiple regression are again following the same principle that we have discussed for the simple linear regression in the last lecture, that we are trying to find out what is the expected value of this y given the input of this x1, x2, x3 up to xm. So, this is the way that we are expressing that that expectation of this target variable y when the specific values of the input variables are given, and this is expressed through this linear equation, as we are now referring to this linear regression, and that linear regression is that beta naught plus beta 1 x1 plus beta 2 x2 up to plus beta m xm. So, this so if you recall that in that last one we are having only one input and we are using this beta naught and beta 1 x, and there are only two parameters for this regression over there, beta naught and this one coefficient with that input variable. So, as you can see here there are m different inputs. So, our this beta naught, beta 1, beta 2, beta 3 up to beta m, these are our regression constants, and this has to be determined based on the data that is available to us. And now you can see that for this x1, if there are suppose that n numbers of that group data is available, then we are having that n numbers of x1, n numbers of x2, n numbers of xm. So, through those points, through those n points, we have to fit one plane surface. Surface obviously when we mention we are referring to the context of this two input variable in a 3-dimensional case, and obviously that concept can be extended to the higher dimension. For example, here it will be the m dimensional space that you can imagine. So, these constants are to be determined, and that is the basic underlying thing in this multiple linear regression as compared to the simple linear regression where the number of input was only 1. So, thus this regression analysis determines the estimate for beta naught, beta 1 up to beta m, and that s y square, that is the variance of this y given this x 1, x 2 up to x m based on the given data x 1 I, x 2 I up to x m I, and I varies from 1 to 3 up to n. So, this I, that the subscript that is used here, that is basically represents the number of data that is available to us, and this 1, 2, 3 up to m represents this. So, this m represents that how many input that we are having. Now, this s y square given x 1, x 2, x 3 up to x m is that the conditional variance of the target variable, that is y. So, this conditional variance should reduce with respect to this unconditional variance, which is that s y square, and how much is this reduction, that we can relate through the so more the reduction is better the model. And at the end of this lecture, as I was discussing, that at the end of this lecture we will see that how that information is related to that correlation coefficient. So, after some rearrangement of this equation that we have seen here, that is expectation of y given this x 1, x 2, x m equals to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta m x m. This we can rearrange to get the another form of such of the same equation, which is equals to the alpha plus beta 1 into x 1 minus x 1 bar plus beta 2 into x 2 minus x 2 bar, like that up to beta m into x m minus x m bar. So, this this x1 bar, x2 bar or xm bar is the mean of that particular input or that particular variable. So, as I was telling that x1 is that first input variable and this I can vary from 1 to n. So, we are having n data and this that mean of that input variable is represented as this x1 bar. So, basically this alpha what you can see now is basically one adjusted constant once again, including that beta naught, and if we see that. So, alpha can be expressed like this, that alpha equals to beta naught plus beta 1 x 1 plus beta 2 x 2 bar up to beta m x m bar. So, this once we know this data, basically this x 1 bar, x 2 bar, x m bar are known, and so once we get the estimate of this beta 1, beta 2, beta 3 up to beta m and alpha, with the help of that we can estimate that beta. So, here in this expression what we can target is that we will first estimate these parameters alpha, beta 1, beta 2, beta 3, beta m, and with the help of this we will get what is the beta naught, and we will get the final form of this regression equation like this. So, now again we will use that same principle that we use there in the simple linear regression. There basically, as I was telling, we are fitting a straight line and we are trying to minimize that error, and that error means what is the error with respect to the modeled target variable and what is the observed. So, here also what we will do, we will estimate these parameters in such a way so that estimate of that variable y and the observed y, their difference should be minimum. So, this difference now what is actually observed and what is estimated from this model is basically is your error, and that error we should make it square, and once we make that square and sum them up. So, that is a sum of square error, and with respect to that we will take the partial derivative with respect to all this constant that we are supposed to determine, and that if we equate to 0 in the sense that we are minimizing that error, sum of square error, and we will get some simultaneous equation and we can solve this thing that we will see now. So, now here again if we recall that again from the simple linear regression, there are two cases. One is that the variance of y with respect to that input variable, whether that is constant or that can also vary. So, that in case of the simple linear regression, we have shown one case that where that variance can even vary with respect to the range of the input variable x. So, similarly here also with respect to the which zone we are talking about with respect to that the input variables, if that the variance of this target variable, that is y, is constant irrespective of this which zone that we are talking about of the combination of this input variable, that is y, that is x 1, x 2, x m, then we can say that that is either constant, that variance is either constant or that can even vary. But if it varies, then that form, that is how it is varying over this zone, so that function should be known. So, now if we assume that first case, that is that the conditional variance is constant, then the sum of square error of the n data set points can be calculated as this. So, this y I is our actually observed target variable, and y I prime is that modeled variable, that is we are getting from this regression equation. So, difference between them, square them up, and then sum up for all the individual observation, that is n numbers of observations are there. So, this quantity is giving that sum of square error. Now, if we replace this one, this y I prime, then it will come that this alpha minus beta 1 into x 1 I minus x 1 bar minus beta 2 into x 2 I minus x 2 bar minus like this up to beta m into x m I minus x m bar, and full whole quantity square. So, this will give you that sum of square error. Now, we have to minimize this delta square to obtain the estimate for the regression coefficient. So, to minimize this one, as we have seen in this simple linear regression also, that with respect to all this constant, we have to make it equal to 0. Similarly, that for this say delta this delta square dou alpha is equals to 0. Similarly, for this beta 1, beta 2, beta 3 up to beta m, like that all these partial derivatives should be equals to 0. So, if we take this first one, that dou delta square dou alpha, and then we can take this one this partial derivative, and that if we equate to 0, then the form comes like this, where we can, if we take this summation inside, and we can see that this x1 i minus x1 bar, basically if we take this difference and sum them up, obviously here power is 1. So, if we take that sum them up, this will become 0. So, like that for this x2, x3 up to xm, all these quantities will become 0 as it is written here. So, for all these quantities it will become 0. So, now if we just put this expression, these values here, then it will reduce to this form like this, that alpha cap is equals to summation of y I, obviously I from 1 to n divided by n. So, this is basically the mean of that observed target variable y. So, this estimate of this alpha from this way, we can see that it is the mean of y. Now, the remaining there are remaining m equations are there, which are the partial derivative with respect to all m betas, basically this beta 1, beta 2 up to beta m, and there also we will get that alpha, and this one, this expression, the estimate of this alpha, if we just put it back. So, we can get a set of equations like this. There is this beta 1 estimate of this beta 1, this hat means here the estimate of this beta 1 multiplied by x1 i minus x1 bar whole square plus beta 2 bar this x1 i minus x1 bar into x2 i minus x2 bar, like that all this plus and up to this beta m, which is equals to that particular variable x1 I minus x1 bar multiplied by y I minus y 1 bar. So, this summation for this all n observation. And so, this is the first equation, like that we can get all other equations, and up to that mth equation will be like this, that beta 1 cap into x m I minus x m bar into x I minus x I bar, like that for this beta 2, and at beta m it is x m I minus x m bar whole square, which is equals to x m I minus x m bar into y I minus y bar multiplication summation for 1 to n. So, one thing that you can see here, when you are taking the partial derivative with respect to beta 1, that is the first equation. So, this quantity is becoming square, basically this quantity, that x 1 I minus x 1 bar is basically getting multiplied for all this left hand side of this equation for all other variables. So, these things x 1 I minus x 1 bar, this one is there for all this entry, and here also right side also you can see that this is the target, this is related to the target variable y, and this one is that related to that for which constant we are taking the partial derivative. Here it is for beta 1. So, you can see that this quantity is this, like that for this last one, which is the mth equation, the partial derivative taken with respect to the beta m. So, you can see that what we have seen for the first expression is here, that is x m I minus x m bar square. So, this quantity is multiplied with this all other expression in the left hand side, and also on the right hand side with which is this function is related to the target variable, which is also multiplied by this x m I minus x m bar. So, similarly, you can see that for other variables also. So, if it is for this beta 2, then the first quantity will be that x 1 I minus x 1 bar multiplied by x 2 I minus x 2 bar, and the second quantity will be x 2 I minus x 2 bar whole square, and like that right hand side will be x 2 I minus x 2 bar multiplied by y I minus y bar. So, so in this way these are the simultaneous m equations are there, and there are m unknowns. So, thus we have the m linear simultaneous equation with m unknowns. which can be solved for the values of the coefficient beta I. So, beta 1, beta 2, beta up to beta m, and obtain the least square regression equation. And so, once we get those estimate, finally the expression, that linear regression expression that we are getting is that alpha cap plus beta 1 cap into x 1 minus x 1 bar plus up to this beta m hat, means that is the estimate of beta m into x m minus x m bar. And now, if we write in terms of this first equation, that is the beta naught hat plus beta 1 hat x 1 plus beta 2 hat x 2 plus beta m hat x m, and this beta naught is now that the beta naught hat, that is the estimate of this beta naught equals to alpha hat, estimate of this alpha, minus beta 1 hat x 1 bar minus beta 2 hat x 2 bar minus beta m hat x m bar. So, this is the final expression for this multiple linear regression that we will get. And the conditional variance, given that all those input variables will be that delta square, this is the sum of square error divided by n minus m minus 1, which you can see that this delta square is the summation of this y I minus this alpha hat minus beta 1 cap. So, this is the sum of square error divided by n minus m minus 1. So, now you recall that when there is only one input was there in case of the simple linear regression, if you recall that equation for this conditional variance was delta square divided by n minus 2. So, there m was only 1. So, one input was there. So, if you put m equals to 1 here, you will get the same expression, that is delta square divided by n minus 2. So, if m increases, so here the m is more than 1. So, you have to put that value, and this n is this number of data points that is available. So, this is one unbiased estimate, and why we have already discussed earlier that unbiased estimate. So, that number of degrees of freedom is lost. So, that should be reduced. So, here you see that n minus m. So, there are m estimates are there for this x 1 bar, x 2 bar up to x m bar. This is the estimate that we are there are those estimates are there. So, m degrees of freedom is lost here. Again one more parameter here, the alpha hat is there, that we are calculating. So, it is that basically m plus 1 degrees of freedom is lost, and in case of simple linear regression there are two constants over there, that is to estimate. So, 2 degrees of freedom was lost there. So, it was delta square divided by n minus 2 in that simple linear regression. So, this is the unbiased estimate of the conditional variance of y. And similarly, if that corresponding standard deviation is the positive square root, you know. So, this is delta by square root of n minus m minus 1, where n is the sample size and m is the number of dependent variables. So, now we will take up one problem here. So, you can see that there are many application can happen in the civil engineering problem. So, if you just see here for this particular problem here, so this could be any, say for example, that we are talking about the what should be the temperature with respect to its altitude and latitude. Generally, if the altitude increases, we know that it will the temperature will decrease, and if the latitude also increases, the temperature generally decreases. So, suppose that type of data if we just take here. So, this is the number of observations, the 10 numbers of observations are given, and this is the target variable of this y. So, you can see that it is 45.2, 50.1 like this. So, these are the 10 observations that you can see here, and these are the inputs of this. Say here we have taken the two inputs only, x 1 and x 2. So, here m is equals to your 2. So, I can write that m is equals to 2 here. So, this is your x 1 and this is your x 2. So, this is up to this, you can see that this is your data that we are getting. Now, to get that estimate, if we want to know that, So, these 3 columns that you can see is the input. So, first thing that you have to calculate is that this could be used in a general spreadsheet, just to explain that how these things can happen. So, first what we can calculate, that this x1 I minus x1 bar, that mean that we calculated here. So, that square up for this one. So, basically this x1 minus this mean is calculated here. So, yeah, so this minus this, that square will be give you this value, and similarly for this all such values we can calculate this one. Similarly, for this is for the x2 minus x2 bar, that square that we can calculate, and then this is that your x1 minus x1 mean multiplied by x2 minus x2 minus that x2 mean and their multiplication, because basically this is the column end. So, this entry minus this multiplied by this entry minus this mean. So, this is your mean row that you can see here, and this is the summation, and there are 10 observations are there. So, this 2210 minus this value multiplied by this 38.2 minus this 37.13, this is the mean. If you multiply this, we will get this one. Similarly, this column is for your that x1 minus x1 mean multiplied by yi minus yi mean. So, if you see this one, so here also basically, so this minus this mean multiplied by this minus this mean, we will get these values. So, here again this column, if you see that, then this y2 minus y2 bar multiplied by yi minus y bar. So, this x2 minus this x2 mean into that y minus y bar, that multiplication if we take, we will get this value. Similarly, for all these 10 observations we have calculated, and the last row that you can see, this is their summation. So, up to this we can just calculate first directly based on whatever the data that we are having, and then you know that estimate of this alpha is equals to your that y mean. So, this is directly the 51.7 that we have seen for the mean for this y. Okay. Now, the variance of y also we can calculate, whatever the we have seen this that y, that we can calculate the variance of that from the sample estimate that we discussed earlier, you will get this 22.78. Now, this expression, now if we refer to this equations here, that is that just here you have to put that m equals to 2. So, this value minus this square multiplied by this beta 2 into this one, this value will be equal to this one. So, all these quantities has calculated now here. So, using these informations, these quantities that just now what we have calculated, we will just set. So, here there will be 2 simultaneous equations. So, these 2 equations are written here. So, this is your that first quantity multiplied by beta 1 plus this quantity multiplied by beta 2 is equals to that right hand side. Similarly, so this is the first equation, this is the second equation that we get, and if we solve this 2 equations, and there are 2 unknowns, beta 1 and beta 2. So, you will get that this is your beta 1 and this is your beta 2. Beta 1 is minus 0.0032 and beta 2 is minus 0.422. So, with this estimate and with also that alpha also we know. So, that beta naught we can calculate, that is beta naught as we have seen here, that beta naught is equals to your alpha cap minus beta 1 hat x 1 bar minus beta 2 hat x 2 bar. So, like if we use that one, so beta 1 minus this mean of this that alpha minus beta 1 estimate multiplied by the mean of x 1 minus beta 2 estimate into that x 2 bar, then we will get what is your beta naught. So, once we get these 3 information, that is your, this is your beta naught, this is beta 1 and this is beta 2, then we are getting this full expressions like this, that y is equals to your 72.4, which is your beta naught, minus 0.422, this is the estimate for this beta 1, multiplied by x1 minus 0.0032 x2 is that expression. Now, if we use this expression and use this, what is this input, then what we are getting, this is the estimate of this this y. Basically, we can say that is the expectation of y given x1 comma x2 equals to this. So, this quantity is basically is calculated in this column. So, which is the estimates for this y. So, I can write that y prime, and these are the error. So, this y minus y prime. So, these are the error and that square. So, if I just square for all these 10 observations and sum them up, this is basically is your that capital delta square that we are getting here. So, once we get that capital delta square, then we can calculate what is the conditional variance. This conditional variance means, as we have seen, that s y is square on given that x1 comma x2. So, this if we calculate, we will get this 17.274. So, and the conditional standard deviation is the positive square root of this one, which is 4.156, and the r square value that we get is that 1 minus. So, how much is this reduction? So, you can see that this variance of y, that is the unconditional variance, was 22.78 and the conditional variance is 17.274. So, that we can see here, and this, so that r square is so that 24.2% has is the reduction. So, if you want to see this one in this larger font, you can refer to this Excel file, which you can see here more clearly whatever the calculation that we have done. Okay. So, with this we can say here once again that now when should I say that this model that what we have, whatever we got, that is strong enough or not, that we will see that in terms of this correlation coefficient that we are going to discuss now. And again this will be this is basically that a part of this hypothesis testing. Once we estimate one parameter, and that parameter whether that is significant or not, that can be tested through this hypothesis testing that we have covered earlier. So, through that hypothesis testing, we can see that how significant that estimate is, and the hypothesis testing was covered in the earlier lecture. So, here we will go to that nonlinear regression, and this nonlinear regression is essential when we see that when that linear. So, in case of this simple linear regression, we generally get one straight line, and for this, say if there are two inputs, we get a straight surface. But if that straight line or the surface which is the linear in nature may not express the variability fully. So, what we get sometimes is that sometimes the predictions based on such linear relationship may overestimate in certain ranges of this variable or underestimate in other ranges of this variable of this expected result. So, in such cases, a nonlinear relationship between the variables could be more appropriate. The determination of such nonlinear relationship on the basis of the observational data involves the nonlinear regression analysis. So, basically in this nonlinear regression, what we do is that the expectation of y on condition x is equals to a function like this alpha plus beta gx. So, this gx is a predetermined function of this x. So, what we can do is that we whatever the input x is there, we will get another new variable through this gx, and that variable I can use with respect to this y and follow again that either the simple linear regression or multiple linear regression, because once you have converted, then you can see this this form of this equation is a linear regression form. Say for example, that if that gx is equals to that log natural of this x, then we can define a new variable x prime of gx to have that expectation of y given x prime. Now, it is the converted variable is equals to alpha plus beta x prime, which is now similar as the linear regression equation, and can be solved accordingly. We will take up one example. The average all day parking cost in various cities of India is expressed in terms of the logarithm of the urban population, that is modeled with the following nonlinear regression equation. The expectation of y given x is equals to your alpha plus beta ln x with a constant variance y given x, where y is the average cost in Indian rupees for all day parking cost in hundreds and x is the urban population in thousands. So, this relationship, if sometimes what happens if we just plot the data, that is the, say for example, here the y and x, if we plot it through a scatter plot, that time this nature can be visible whether a linear or a nonlinear expression should be more appropriate or not. So, these are some initial guess. So, based on that, if we see that this log transform of that x might be the better estimate for this case. So, that is why the proposed equation is that alpha plus beta of log natural of that of x. So, we have to estimate that alpha and beta. So, as we have told that we have to first transform that values of this urban population through this log natural function, and then we will get a new set of this new variable, new observation in place of this x, and then we can follow whatever we have seen in the linear regression equation. So, here there are 10 cities are there. These expressions, that is a xi that in that thousands, that what is the population that is shown here, and this is a yi in hundreds, what is the parking cost for all day parking. So, with these two data, what we can first do is that, so this xi, that is the input that is converted through this log natural, and we get this expression. So, using this one as the input, so we have to model this yi. So, all those quantities that we required for this least square estimate, that is that should be estimated, only in place of this xi we should use this xi prime. So, xi prime multiplied by yi, then xi prime square, then yi square, this we can calculate. So, up to this column, whatever the data that is available, we can calculate, and we can take their individual summation also. Now, with the help of this information, their summation, the summation of xi prime yi, summation of xi prime square, summation of yi square, we can get that what is their mean of this x prime, which is 6.545, y bar is 0.808. So, this estimate of this beta hat, as if you refer to this expression of this least square estimates, then we can get that estimate of this beta hat will be 0.291, and the alpha hat will be minus 1.097, and the variance of this y, which is unconditional, which is your 0.1047. Now, using this alpha hat and beta hat, what we can calculate that that modeled values we can get for this yi. So, this alpha and beta are whatever we have estimated now, and now we will use these inputs, this xi prime as this input as this x, and we will get what is the model estimate for this yi. So, that we will get, and after we get this one, then we can calculate what is their square error. So, this 0.51 minus 0.563 square will give you this value. And similarly, for all 10 observations, it has been calculated and sum them up to get that sum of square error, which is 0.164. Now, using that 0.164, we know that this conditional variance of that target variable y is your that sum of square error divided by n minus 2, and here you know that 2 means that that in number of input variable is 1. So, 1 plus 1 it is 2, that is for just now we have seen for this multiple linear regression that it is that sum of square error divided by n minus m minus 1. so m plus 1 degree of freedom is lost. So, here this 10 minus 2. So, if we calculate this one, so this conditional variance will be 0.0205. So, this conditional standard deviations positive square root of that, which is 0.143, and that percentage of this reduction of this variance. So, this 1 minus what we got for this conditional 0.0205 and what was the unconditional, which is 0.1047, which is equals to 0.804. So, finally, the equation, that final equation that we get, the mean value function on the standard deviation is that expectation of y given x equals to minus 1.097, which is estimate for this alpha, plus 0.291 estimate for the beta into log natural of that x, and conditional variance given the x is constant, conditional standard deviation given that x is constant, which is equals to 0.143 as we have seen, and this r square that we got is that 0.804. So, you can say that here that 80.4% of this variability has been explained through this model. Well, so now we will just take that correlation part that we have discussed earlier, then you know that the correlation is a statistical technique that can show whether and how strongly the pairs of the variables are related. And the study of the degree of linear association between two random variables is called this correlation analysis, and the accuracy of a linear prediction will depend on the correlation between the variables. Now, so we can, in this regression context, what we can say is that if we say that what we have modeled and what we have observed is these two are linearly associated and that linear association is strong enough, then we can say that yes, just now we have seen that in terms of this percentage reduction of this variance in through this r square, which is we can say that, so that much variability can be explained through that developed model. So like that so this accuracy of the linear prediction will depend on this correlation between those variables in a two-dimensional plot. Now, if we just take that only one input here, in case of the simple linear regression, the degree of correlation between the values on two axes is quantified by so called correlation coefficient, which is given by this equation we have discussed earlier, that is correlation coefficient is the covariance between x and y divided by standard deviation of x multiplied by standard deviation of y, and the covariance of x, you know, that is x minus the expectation of x minus mu x into y minus mu y, where this E is the expected value of this operator and COV is that operator means the covariance between these two. So, basically so in that after we develop this regression model, we have to see that what is the correlation coefficient between that what we have observed y and what we have modeled through. So, basically here, even though we are expressing this one just to relate our earlier discussion x and y, basically we have to see it for this y I and that y estimates, that is the y hat from that regression expression. So, now this correlation coefficient may also be estimated by this rho hat. Now, this estimation that we are getting 1 by n minus 1 I equals to 1 to n xi minus x bar yi minus y bar divided by sx sy. So, this one you can see that this expression now can be written as this I equals to 1 to xi into xi yi minus n into x bar into y bar. These are the means of this x and y, whatever we have observed in this data, divided by that sx into sy, where these things x bar, y bar, sx and sy are the sample means and standard deviation of x and y respectively. So, we have seen also that this in the simple linear regression, that the estimate of this beta is having this form of this. So, if you just put this one in whatever in the expression of this rho, then we can get this expression that this rho hat is equals to that beta hat multiplied by this ratio of this sx and sy. So, that ratio between the standard deviation of x and y, standard deviation of x and standard deviation of y multiplied by this beta hat will give you that estimate of this correlation coefficient. So, now also what we have seen that the conditional variance, that conditional variance of y given that x is equals to 1 by n minus 2 that multiplied by I equals to 1 to n yi minus y bar square minus beta hat square I equals to 1 to n into xi minus xi bar square. So, this expression that we have seen in that simple linear regression to express that what is the conditional variance. So, if we just put that that estimate of this beta hat in terms of their correlation coefficient and their variance of those y and x, then this conditional variance that we can write that 1 by n minus 2 this expression, and in place of this beta hat square we can write that this rho hat, sorry, this will be rho hat, the estimate of this correlation coefficient, that rho square multiplied by this sy square and sx square. So, these are the variance of y and this is the variance of x. So, if we just express this this one, then we can write that this is n minus 1 divided by n minus 2 sy square into 1 minus rho hat square. So, this one, this part that we can take and we can express that what is coming is that sy square will come. So, this sx and this one we can relate to this sx square variance, that you know that this is this divided by n minus 1 will give you the estimate of this sx square. So, that can be observed here, and final expression that we are getting is that conditional variance of y given this x will be equals to n minus 1 by n minus 2 into sy square into 1 minus rho hat square. Now, if we can say that this estimate of this estimate if we say that this n equals to 1, sorry, if we say that this n is very large. So, that means that when we say that there are large numbers of observation is available. So, for n when n is very large, then we can say that this quantity can be equated to unity, and that we can say that this will be equals to your sy square into 1 minus rho hat square. So, this is the final expression that we get, which can be approximated. So, this one, this expression for this n equals to large, or for any n, if we just consider this factor to be multiplied, that which can be approximated to this r square for this large n. So, what we have seen earlier, that this r square, that is we have explained in terms of this percentage reduction of this variance, which is equals to 1 minus the conditional variance divided by the unconditional variance, that was the r square, percentage of the reduction, or that there is a percentage how much is explained through that regression model. So, here we can see that for if the n is large, then this quantity can be approximated to this r square. So, what we have seen so far is that if we know that the correlation coefficient between the variables that we are modeling, that is what is your target variable and what is your input variable, if we know that what is their correlation coefficient between them, and if we know that what is their respective mean, then basically what we can do, we can develop we can get the estimate of those parameters of the regression. So, we can basically develop that their regression equation. So, one such example we will just see now, that, and this example is on that from the following results, obtain the two regression equations and estimate the yield of crop when the rainfall is 22 centimeter, and the estimate the rainfall when the yield is 600 kg. So, basically this is the relation between this yield of the irrigation and what is the rainfall in terms of this depth of the rainfall in centimeter, and the mean of this yield, the mean yield is 408.4 kg and this mean rainfall is 24.7 centimeter. So, the standard deviation of this yield is 31.8 kg and standard deviation of this rainfall is 4.5 centimeter, and the correlation coefficient between the yield and rainfall is 0.54. So, these informations are available to us. So, if we know this one, then we have to develop the two regression equation, that is the what is the expression for this yield given the rainfall and what is the expression for the rainfall given the yield. So, these both the equation we can use with the help of this their information of this correlation coefficient. So, let that y be yield and x be the rainfall. So, for estimating the yield we have to run the regression of y on x, and for the purpose of the estimating the rainfall we have to use the regression of x on y, and the information that we know is that mean of this x, mean of this y, standard deviation of x, standard deviation of y, and their correlation coefficient between them. So, this beta x given y, that is when we regress x on y. So, this is that correlation coefficient divided by their ratio of their standard deviation. So, what we get that 0.0764, and on the other hand when we regress that y on x, then that beta coefficient will be 3.816. So, the regression equation for this y on x will be y minus y bar equals to beta y. So, the coefficient when we are regressing y on x, that is the noted like this, that beta y slash x multiplied by x minus x bar. So, that we have estimated 3.816. So, after rearranging this we can get the equation like y is equals to 3.816 x plus 314.145. So, this is the regression equation for the for y on x. Similarly, we can regress the equation of this x on y, which finally we get that x is equals to 0.0764 y minus 6.502. So, with this one, if we use this expression, and then the question was given that when x is equals to 22, what is the yield, that is when the rainfall equals to 22 centimeter, what is the yield. So, putting that in this expression we get that y is equals to your 398.1, and when that yield is equals to 600, then the estimate of this rainfall is your 39.34. So, the estimated yield of this crop is 398.1 kg and the estimated rainfall is 39.34 centimeter. So, this is when this yield is when rainfall is 22 centimeter, and this rainfall is estimated like this when the yield is 600 kg. So, in this lecture, or including this last lecture, we have discussed the regression, different regression technique, including their simple linear regression, multiple linear regression, then nonlinear regression, and their that in terms of this correlation how we can estimate, that we have discussed. So, in this entire module, whatever we have seen in this probability and statistics, we have started with the sample statistics, then we have covered this hypothesis testing, then how to test what the data follows what distribution through this probability paper, and different different statistical tests to test that what is the distribution of this of the parameter, and finally we have covered the regression analysis and correlation. Thank you.